In this video, we start chapter 4, where we encounter our final type of interest that we'll be looking at in this course called a force of interest. So I'll step off the screen. Please copy the material down in your notebook and then press play and we'll resume. All right, so in chapter 3, we introduced this notion of compound interest, where we're getting the interest more than once per year, or maybe less than once per year. Okay, so a time period other than just once a year. So the number of times per year we got interest was denoted by the letter M. So in this chapter, we examine the idea of letting the number of times per year that we compound our interest, that value of M, approach infinity. So monthly would be M equals 12. Daily would be M equals 365. What if we let M go to a billion, a trillion, 10 trillion, up to infinity? We'd be constantly compounding our interest. If we do that, we're compounding continuously, and the interest rate used is called a force of interest. All right? We have some notation for this force of interest. The force of interest at time t years is denoted by a delta sub t, or delta t. That's a lowercase delta, not a capital delta, which is just the triangle. Or your textbook often uses r sub t, though Exam FM tends to use the delta, and I'll tend to use the delta as well. So there's two types of forces of interest. You can have delta t equaling 7% or 0.07, like an actual numerical value. And that would be called a constant force of interest. No matter what the time value is, force of interest is 7%. Or with force of interest, we can allow for varying forces of interest at different times. So our force of interest could be a function of time, such as 0.01 plus 0.03 times t. So at time t equals 2, I get 0.03 times 2 is 0.06, plus 0.01 is 0.07. So at time t equals 2, the force of interest would be 7%. At time t equals 3, though, would be up to 10%. Right? So that would be called a varying force of interest. All right. Now, it's important to know what the definition of the force of interest actually is. It is, you must know this. So let's let AV sub t be the accumulated value at time t years. And I can also denote that as AV parentheses t to indicate that the accumulated value is a function of time. At different times, you'll have different accumulated values. So you can use either one of those. So the definition of the force of interest is it's a fraction. It's the derivative of the accumulated value at time t divided by the accumulated value of time t. Or said the exact same thing, said with different notation, it'd be AV prime of t divided by AV of t, right? This is a somewhat natural definition. The numerator, the derivative of the accumulated value, is telling you the rate of change in dollars per year in your account. Well, if the rate of change in dollars per year is $10,000 per year in your account, if it's me, I'm thrilled, right? That's $10,000 a year that I'm growing at. If it's Jeff Bezos and he has all of his money in one account, if he's only gaining $10,000 a year, if his rate of gain is only $10,000 per year, that's nothing to him. That's like 0% for him, right? So in order to make that rate of change, that derivative, have some context for us, we'll divide by the total amount of money in the account at that time. So that's going to give us a percentage instantaneous rate of change, right? The force of interest. Okay, so that is the definition of delta t. If you're going to take Exam FM, I'm pretty sure they will somehow test your knowledge of that definition. So know it. And for this course, I'm pretty sure I will test your definition of your knowledge of the definition of the force of interest. All right, and since we have a new force of interest, we were also going to pick up a new accumulated value formula, which the derivation will be gone over later. So let's let t sub 1 and t sub 2 be years, t sub 1 before t sub 2. Then the accumulated value at time 2 is given by the accumulated value at time 1 times e raised to this definite integral. The definite integral from t1 to t2 of the force of interest delta t integrated with respect to time. All right. So it's a very different looking formula than the ones you've been used to. Okay. All right. So as an example, determine the accumulated value after 2 years of a $500 investment that earns 3% force of interest. So our force of interest delta t is 0.03. Our accumulated value at time 0, the initial amount we started with was $500. And we'd like to know the accumulated value 2 years later, so AV2, right? Well, so there's the formula from up above. AV2 equals AV0 times e to the integral from 0 to 2 of the force of interest. Force of interest is 0.03. AV0 is 500. The antiderivative of 0.03 is 0.03 times t. And if I plug in t equals 0 and t equals 2, I get to this stage right here. So 500 times e to the 0.03 times the quantity 2 minus 0. And that cranks out to $530.92. Okay. Now, how did I know that the initial time of this investment was at time 0 and 2 years later was at time 2? Well, I didn't, but it doesn't matter. Okay. Let's say I decided the initial investment arrived at time 3. Well, then I would have been after the investment value at time 5, 2 years later. And I would have been integrating from 3 to 5 instead of from 0 to 2. But since 5 minus 3 is the same as 2 minus 0, in this case, it didn't matter. This hinged upon the force of interest being constant, not being a function of time. If our force of interest had been a function of time, such as back here, I really need to know if I am looking at this force of interest between times 0 to 2 or between times 3 to 5, because I would be looking at vastly different interest rates there, right? But many of the problems we'll encounter will have a constant force of interest. And so knowing when you start and when you stop isn't as important as knowing what the duration of the time period you're looking at is. In this case, it was 2 years, okay? We'll do an example in the later videos about using a varying force of interest. And the problem would have to be very explicit as to the starting time and the ending time, okay? All right, however, based on this example, we see something that makes our life slightly easier if we're dealing with a constant force of interest. If our force of interest is a constant, this accumulated value formula actually gets a little bit easier. The accumulated value at time 2 is given by the accumulated value at time 1 times e to our force of interest times T2 minus T1. That's exactly what happened back here. Our force of interest of 0.03 times 2 minus 0 or times 5 minus 3, whatever the two time stamps were. We don't have to do any integration because the antiderivative of a constant is linear. And when you plug in the bounds, you get to this exact formula, okay? All right, and you'll note I've dropped the sub t in the delta because if a force of interest is constant, it doesn't matter what the time is, it's always that number. So we just call it delta, all right? So here's a slightly simplified version if you have a constant force of interest. If you don't wish to memorize this, please don't. This works for all cases. Force of interest constant or the force of interest varying. All right, okay.